Okay, good evening, students. Today we are discussing the grade 12 first term test paper of Visakha Vidyalaya Colombo. Okay, so this paper was given in last year for 2026 A-level students, right, for their first term test. So we're going to discuss the MCQs today, right? So like I did for the Ananda College paper, I'll add the essay paper and the marking scheme of that one to the group. Okay, so you can go through that and mark your answers, right? So this will be a good practice again towards your upcoming first term test exams. Okay, so by this paper we can revise basically the first and second units, and part of third unit is also there in the paper. We'll see, and write a good review for the good questions. Okay, we'll see. So let's start from the first MCQ. So it is asking who concluded alpha, beta, gamma rays are emitted by radioactive sources. So this alpha, beta, gamma radiation was discovered by, right, Ernest Rutherford. Okay, so there's a small mistake in the fifth answer. It should be E, not A. Okay, so Ernest Rutherford starts with E. So that is the answer for the question, right? So this is kind of a very basic and easiest MCQ in the paper. Because it's basically asking about the scientist, right? So let's review other names given here. For example, Henry Becquerel. Henry Becquerel is the one who discovered radioactivity. Okay, so you need to understand the difference, because in this year 2025 A-level exam, they asked about this radioactivity thing. So it's very good to know that one, right? So in front of Henry Becquerel, right, discovered radioactivity. Okay, but even though he discovered radioactivity, he didn't find this alpha beta gamma. Alpha beta gamma was discovered by Ernest Rutherford. Okay, so remember that point was asked in this year A-level exam. Okay, right. So that is the first thing you are going to learn now. And then check the second answer, J.J. Thomson, right? And Thomson, and in front of that answer, you can write what are the things that Thomson related to, right? He's the one who presented golf ball model of atom. Sorry, yeah, plum pudding model of atom, right? Plum pudding model of atom. Golf ball model was presented by Dalton, right? So what are the 5 models? First one, golf ball model by Dalton, and then second one, plum pudding model by J.J. Thomson. Third one, nuclear model or planetary model by fourth model is Bohr. And the fifth one is quantum atomic model, the one we are now studying. Right? And like I said, J.J. Thomson related to the plum pudding model. And the second one he related to is he's the one who discovered electron, right? And E over M ratio for the electron. And then again, he is related to this discovery of isotopes, right? That point was discussed in last week. I hope you remember. Aston and Thomson are the two scientists discovered isotopes. Okay, right. Then you have Millikan, Robert Millikan. Third answer. Millikan is the one who found the charge of electron. So right in front of Millikan, charge of electron. Okay, charge of electron. And the fourth answer, Max Planck. Planck theory, or you can say electromagnetic radiation is divided into actually a collection of energy packets. Remember, that is the Planck theory, quantum theory. Okay, so he called that energy packet as quanta. Okay, so Planck's quantum theory. And like I said, Rutherford also is the answer here, alpha beta gamma radiation discovery. And not only that, Rutherford is related to several other things, right? Example, like I said earlier, he's related to this nuclear model or planetary model. To present this planetary model, he conducted an experiment earlier with his 2 students, and the experiment was gold foil experiment. Okay, remember that too. And then you can write again near Rutherford, he's the one who discovered proton. Okay, proton. So like that, there are several things Rutherford also associated with. Okay, so like that. So those scientists and the summary is there as a table in your tute and at the end of the first tute. So study that one again and again. Will be a compulsory MCQ in your first term test. Okay, and these points can ask in your A-level exam also. Like I said, this year they asking about this Becquerel and Rutherford, the radioactivity thing. Okay, I'm telling that point again, so mark and highlight that one. Becquerel is the one who discovered radioactivity. Okay, but he didn't discover alpha beta gamma. Alpha beta gamma was discovered later by Rutherford. Okay, so that point is very important. Because these alpha particles, by now you remember, is used in several experiments, right? So it's important to remember. So answer for the first question is answer 5. Right, now let's go to the second MCQ. It is asking the quantum number set for an electron in outermost subenergy level of the cation with +2 charge formed by the element with atomic number 23. Okay, so we'll do that one in the board. So atomic number is 23. So what is this element? If you refer to a periodic table, you will see, right? If you start from scandium, scandium is the 21st element. Then titanium, 22. Then you have vanadium. This is the atomic number 23. Okay, vanadium. Then it is telling the 2 plus ion. So it's not vanadium atom, it is vanadium 2 plus ion. So this question is asking about that one. Outermost energy level of vanadium 2 plus ion. So underlying that the +2 charge and atomic number 23, those two things are telling you about vanadium 2 plus. So remember that. Okay, I mean vanadium 2 plus. Now to answer this question is not that difficult, right? But for in the sake of writing the review, I'll give you the electronic configuration from the beginning. Okay, so then that will be a good way to write your review, right? So atomic number 23. So electronic configurations, how do we write? Start from 1s, right? So vanadium atom 1s2, 2s2, 2p6, 3s2, 3p6, then 3d. Yeah, then up to here you have 18 electrons. Up to here you have 18 electrons. So now you need to fill 5 more electrons now. So before filling 3d, we all know 4s2 is filled. So with 4s2 it becomes 20 electrons. So the remaining 3 electrons will be filled to 3d. So this is the configuration of vanadium atom. Okay, so we can simply remind this one in our earlier theories. So except for copper and chromium, except for these two metals, all other metals are having there's a small relationship. If this is 23, 3 will come to the D. Okay, because they all up to 20, they fill 4s2. After that, the remaining electrons are put to the D sub-energy level. Okay, so for example, if I take cobalt, atomic number 27, so it will be what? 3d7 4s2. This 7 comes here. But this is not true for the chromium and copper configuration, because you know they show Aufbau deviations. They borrow electrons from 4s and stabilize their D sub-energy level. Okay, right, now what we need is vanadium 2 plus, right? Not vanadium. So when it is making this 2 plus ion, it has to remove 2 electrons. So where these 2 electrons are removed? It is removing from the outermost sub-energy level, which is 4s, right? First electrons are removed by 4s. So when it is making vanadium 2 plus, then the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6 and 3d3. These 2 electrons are removed to become 2 plus ion. Understand? Now, what is your outermost energy level? Now your outermost energy level is 3d3, 3d. Okay. So now the question is asking the quantum set for that. Okay, so this is an exam level question. Not a difficult one, not a very easy one. So some moderate question. So student has to identify the configuration. So after identifying, it's not over yet. You need to go to the what do you call this one as quantum numbers also, right? So what are the quantum numbers? So it is 3D. 3D. So first main energy level is third energy level. So n should be 3, and it is D, no? So D sub energy level is written by the azimuthal quantum number or L by 2. So it is 3 2. Understand? So there's only one answer with 3 2, which is the fourth answer. That should be your answer here. Is that clear? Fourth answer. Fourth answer. So N equal 3, L equal 2 is the answer. So you can't give us comment about the magnetic quantum number because you know there are 5 orbitals. So we usually draw these 3 electrons like this, but it's not a rule. These 3 electrons can be basically anywhere. I'll give you one example. These 3 electrons can be like this too. Okay, so you can't say it exactly, but only one answer contains 3 2. So then that should be your answer. Understood? So L is the magnetic azimuthal quantum number. If L equals 0, it is S. If L equal 1, it is P. If L equal 2, then it is D. That's the idea. So we have done enough questions with this theory. I hope it is clear to you. Okay. So what are the two things important in this question? Finding the electronic configuration of metal ion and then thinking in related to the quantum numbers. Those are the two things. Okay. Master that one. Right, good. Now let's go to the next question, third one. Which of the following chemical species can have highest boiling point? Highest boiling point. So now these are good questions. Okay, so especially in these Colombo schools, what I see, they give some nice questions time to time. Okay, so now look at this one. This is also a good one. Okay, so they are asking the boiling points. So boiling point is some theory that we discussed under the unit 2 for now. Okay, so if the intermolecular attractions are powerful, then your boiling point will be higher. So then you can write, what's the first point you have to think? Intermolecular attractions. Okay, so for the third question, you can write like this. If intermolecular attractions are higher, or you can say strong, then your boiling point will also be high. Then you need to think which one has the best intermolecular attractions out of the given 5 answers. Let's go and see again those 5 molecules. The molecules are NO, then Kr, krypton, which is a noble gas. Then you have Br2, then you have ICl, and then carbon monoxide, CO. Okay, right. Now let's explain. Now, if you go to this NO and CO, both are polar, right? So this is no need to draw the structure, but anyway, this is the structure you will get, a single electron. So this is polar. You can see electronegativities of 2 elements are different. Okay, so dipole moment will be there from nitrogen to oxygen, the polar molecule. And then this one also polar, ICl. This is also polar molecule. And here the dipole moment will be there from iodine to chlorine. Chlorine is more electronegative. And then your carbon monoxide is also polar. Carbon monoxide is also polar. There also the dipole moment will be there from carbon to oxygen. So all these 3 molecules are polar. You know that polar molecules can form what? Dipole-dipole interactions. Dipole-dipole interactions. But it is not the only interaction that molecules can form. You can see some non-polar molecules are also there. So all these molecules can form, including non-polar molecules, they all can form what? All molecules form London forces, or in other words, we say IDP, induced dipole interactions. Okay, so then you need to think about that too. Okay, so that's why it is a good question. Not only deciding electronegativity difference, and that one is not enough, Lama. Okay, you have to think about, okay, the London forces too. London forces too. Okay, so then London force's strength depends on several factors. So the first and most important factor is the size. If the size is higher, then it has more surface area. More surface area. And then, or in other words, you can say more electrons are there. So then there will be more induced dipoles and have more London forces. Okay, have more London forces. Then you have the shape and everything are there, but those points are not important for this question. So this question you need to focus on this size. So which one is having the highest size? You can see it's too obvious. ICl. ICl. Why? Because it's a larger molecule. Iodine is a very large atom. It's in the group 17. It's the lowest, the last element in the group 17, right? What we discussed. You know the group 17 elements, Lama. If you look at the periodic table, you will remind this one. Fluorine, chlorine, bromine, iodine. See, iodine is the last one. And chlorine is somewhere a little bit above that. Okay, but this one will not have that much boiling point. Why? Because both will have kind of similar relative molecular masses, but this one is non-polar. These two are non-polar. So they have London forces only. So think about this one, right? Understand? Okay, so what is the theory you need to understand now? To check the boiling point, see which molecule can form better intermolecular interactions. Okay, which molecule can form better intermolecular interactions, right? So you have given 5 molecules and you can see 3 of them are polar. So polar molecules can form London forces and dipole-dipole interactions. They can form both, right? And then you need to think about the London forces, which polar molecule out of these 3 can form more London forces. So obviously it has to do something with the size. So the one with the largest size out of the polar molecules is ICl. So then this ICl will form DP and more London forces. Okay, you can write this one. And London forces are also high because of the surface area. So that's why this comes as the answer. Okay, can I see a hand raise? How many of you got this answer? Third question, answer 4. Okay. Okay, very good. Then let's go to the next question. It's another one similar to this. Which of the following molecules do not contain all atoms on same plane? All atoms on same plane. Okay. So I'll draw the structures of these molecules and then explain. So your answer will be, Lamai, answer 4. Answer 4. That means other molecules will contain atoms in the same plane, right? Others will contain atoms in the same plane. We'll see. So the 5 molecules are BeF2, and then you have XeF2, BF3, and SF4, and XeF4. XeF4. Right, now let's draw and explain. But when you are doing this in exam, right, some students can do this question without even drawing any molecule, right? So that's really good. So because they can think about the structure and come to a conclusion, right? So anyway, I'll explain that too, right? But let's go to the drawing. So this is beryllium is making only 2 bonds now. So beryllium fluoride is a linear molecule. So then all molecules will be at the same, atoms will be at the same plane, same line also, right? And XeF2 is a kind of a famous one. Last week also we could draw this. And it is another linear molecule but derived from trigonal bipyramidal electron pair geometry. So this is also linear. And then you have BF3, trigonal planar molecule. So all molecules, all atoms will be in the same plane. And then you have SF4. SF4 is something like this. Now you can see here clearly these ones I'm connecting with the dotted line are in one plane, and these other two fluorine atoms and sulfur are lies perpendicular to that plane. Okay, you remember axial plane and equatorial plane for trigonal bipyramidal geometry. So these two fluorine atoms and the lone pair lies in the equatorial plane, and these two fluorine atoms lies in the axial plane. Okay, so it is not in the same plane. So this is our answer. Then let's do about XCF4. It's a square planar molecule. Square planar molecule. So all fluorine atoms and xenon lies in the same plane. So good question. Good question. Okay, so let's write their shapes. This is linear. This is also linear. But this linear derived from trigonal bipyramidal electron pair geometry. Okay, and this one is trigonal planar. This is seesaw. This is seesaw. And then this one is square planar. Square planar. And this one is derived from octahedral electron pair geometry. Okay, so now I said earlier, some students can do this question even without drawing anything. So how do they do it? So they just think about the molecule in this way, right? So it is SF4. SF4. Now they think sulfur has 6 valence electrons. Isn't it? That's a point we all know. Sulfur is in the group 16 and it has 6 valence electrons. Okay, 6 valence electrons. So from these 6 valence electrons, fluorine will bond with 4. Okay, because always fluorine makes single bonds. They know that one with the practice. So there will be 4 single bonds and 4 electrons of sulfur will be participated for bonding. So then they will see 2 electrons are remaining. So these remaining 2 electrons will be there as a lone pair. So one lone pair and these 4 bonds coming as 4 bond pairs. Okay, so they think and they get the total. So there are 5 total repulsion units. So then it will be trigonal bipyramidal. Then it's continue. So it will be trigonal bipyramidal and there will be one lone pair. So the shape is going to be seesaw. If the shape is seesaw, it's too obvious. The atoms, all atoms will not be in the same plane. Some will be there in the plane and other will be perpendicular to that plane. So that's how they think. Understand? So any structure that I draw here, so I also use the same method. Okay, so you can follow our ordinary method that counting the valence electrons and the other steps for the Lewis structure, but by now try to practice quickly to draw the structures quickly. But still, let's say some students may be struggling with this one. So for them, I'm telling, so okay, you have time. So start properly, right? Don't hurry to draw these quickly, right? So just take it slowly and do it, and with the time you will be doing it fast. Okay, because before 2027 August, if you can do this, right, it will be enough, right? So but don't take that much time. So start now. Start now, because students are doing this, some of them are doing this. So that means anyone who follow the theories and the advices properly can do this. Okay, good. So answer for this question also answer 4. Right, good. Then go to the question number 5. Question number 5. In question number 5, they ask the increasing order of second ionization energy. Have given some elements: sodium, magnesium, aluminium, silicon, and there is another element, bromine. Bromine. So that's why this question is kind of a good one. Here's the way you have to think. Okay, so you are obviously not memorizing values, right? So then you have to think in this way, the way I'm telling, right? So asking for the second ionization energy. So first of all, take the graph for the first ionization energy. Okay, so this is the graph. In this graph, sodium lies right here, and magnesium, aluminium, and silicon like this. And your bromine, where is bromine is? Bromine is not an element in third period. So these elements are in third period. So bromine will be there in fourth period. Fourth period. And it will be having a little bit lesser ionization energy. Ionization energy of bromine will be lower than ionization energy of chlorine. That's the point you know. Okay, so chlorine first ionization energy will be higher than bromine first ionization energy. And chlorine second ionization energy will be higher than bromine second ionization energy. That's the thing you know. Okay, nothing else. So then when they are giving the answers, now it's a good question, right? When they are giving the answers, they didn't expect for you to know where the bromine is. If you think only the other four elements in the third period, then it is enough. Understood? So now let's worry about these four elements then. These four elements. Now this is for the first ionization energy, no? IE1. IE1. So how do we get the IE2? So second ionization energy, the usual method is you have to come one backward in this graph. Coming one backward, that means sodium second ionization energy will be right here. Okay, and magnesium second ionization energy will be here, and aluminium will come to this place, and silicon will go to aluminium's place. Okay, so why I'm writing like this, I'll explain using sodium. If you take first ionization energy of sodium, you are removing this single electron, the outermost electron. Removing it is relatively easy. But when you remove another electron, you have to remove that electron from sodium plus. Sodium plus is a stable configuration containing ion because it is having 2s2, 2p6 noble gas configuration. Understand? So removing electron from sodium plus to make sodium 2 plus is difficult. So that's why it is relatively at a higher place. Now actually this electronic configuration belongs to what? Belongs to neon, the noble gas. That's why sodium is put to this neon's place. Earlier here it was neon. Now can you understand why we should come one backward? Because after removing one electron, this ion will take the electronic configuration of the previous element. Okay, here it is neon. So then the difficulty will be similar to that previous element ionization. Okay, so that's why we are coming one backward. Right, and then if you apply the same logic, if you want to get the third ionization energy, what you should do? Come two backward, like that. So this theory works almost all the time. So they only ask questions also where you can apply this theory. So don't worry. Don't try to, go to the root and check whether this theory is correct always. No, don't need to do it. Okay. So in your A-level exam, you are just comparing and finding answers. Right now, according to this one, you can see the locations. Sodium is the highest one. And then you have what? Aluminium. Then you have silicon. Finally, you have magnesium. Okay, you don't know the location of bromine according to what we learn in theory class. Okay, now let's check whether there is any answer contained this way. So its sodium should be the highest one. It should be like my question also should be changed. It is decreasing order, okay? Decreasing order. And sodium is the highest one, true. Then you have aluminium, okay. Then silicon and magnesium. Right? Now check the answers. You can eliminate answers too. Okay, you can eliminate answers. So sodium should be the highest one always. So there are only 3 answers starting from sodium. In all those 3 answers, you can see the last element is bromine. So that means you don't need to worry about bromine. Okay, in answers it is already given. Right? And then you have, you can eliminate the answers. So answer 2 and 4, they start from sodium, but the next element is magnesium. It can't be, no. Magnesium should be the lowest ionization energy element. So even without drawing this graph, You can get the answer by just eliminating answers. Okay, so this is a good design for the question. Okay, so what is the answer again? Answer 3. Okay, answer 3. So can I see how many of you got the answer 3? Can I see a hand raise? Answer 3. This one. Okay, good. Okay, very good. So if you check, actually I checked the bromine ionization energy, second ionization energy, because I want to give you a review now. So actually the bromine second ionization energy is not according to the way they have given in the question. Okay, so it will be a little bit higher than magnesium or as I remember silicon ionization energy too. Because you know, chlorine is right here, no? The first ionization energy, chlorine. And chlorine second ionization energy will go to this place where the sulfur was. And our bromine, this is Cl plus, you can say, Cl plus. And our bromine will be little bit lower than this, somewhere here, bromine plus. Okay, so then we don't know where it is exactly, but it will be little bit low. So then you can't exactly say, and the questions are telling it is the lowest. That part is not true. Okay, and put a stand right, even though they have taken that as in the answer. Say bromine is not the lowest. Lowest here. Okay, lowest here. It will be little bit lower than chlorine ionization energy. Remember that point. Okay, remember that point. We can't find which one exactly the lowest, right? Without the values. When rereading, we have to address those things too. Question is a good one, we know, but it's a small thing if you go to the exact fact. But still, you can get the answer, right? Answer. Here you have to select is answer 3. They are not going to give all for this question, okay? Right, go to the next question. Sixth one, not a difficult one, asking the electron pair geometry and shape. Electron pair geometry and shape. XeO2F2. 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 Now let's try that one according to our Lewis method, because in every paper I'm trying to revise all theories, right? And for every student at any level, right? So let's say how to start this one with the basic Lewis method. So first thing you need is a skeleton structure. Skeleton structure. And you can see there are 4 bonds. And then take the valence electrons. From xenon you have 8. And from 2 oxygen you have 16. Sorry, 6 into 2, 12. And from 2 fluorine you have 7 into 2, 40. So then you have 34 valence electrons. From these 34 electrons, you have to subtract 8. 8 for the bonds. Because you have already represented that 8 now. So then it is 26. If you divide 26 by 2, you will get 13 electron pairs. So those 13 electron pairs, you have to start by fluorine and apply 3 per each atom. So 12 is given. And the remaining one, you need to put to the xenon. Okay, so then the octets are all completed. Then you can check the charges. When you check the charges, you will see minus is there, and xenon will have +2 because it's supposed to have 8 electrons, but you can see only 6 are there. And since it can violate octet rule, it will form multiple bonds with oxygen to minimize charge. So this is the structure of this molecule. Okay, and there is a lone pair here. So now, what are the geometries, electron pair geometry and shapes? And here you can see one lone pair is there. And if you check the bond pairs, there will be 4 bond pairs because we take this one as one bond pair, right? And altogether you have 5 repulsion units. And then the electron pair geometry will be a trigonal bipyramidal. Trigonal bipyramidal. and shape will be seesaw, which you have one lone pair. So how do we draw this one actually? So then you can start like this. Let's put the two oxygen atoms here and fluorine, and the lone pair. You can put fluorine to the perpendicular plane too, no problem. Okay, so this is the structure. So what is going to be the answer? Let's check. Trigonal bipyramidal and seesaw. Answer is answer 1. Answer 1. I hope most of you got the answer. Right, now let's go to the 7th question. That was easy one. Now let's see the 7th question. Decreasing order of the electronegativity carbon atoms. Okay, of the carbon atom. So the given ones are CF4, CCl4, CF4, CCl4, and then you have CH2O, CH4 and HC. So since they are asking the electronegativity of same element, carbon, you have to use this scope method. Remember, scope method. Scope. So S stands for the S percentage. You have to find the S percentage first of all. S percentage. And then you have to check the charge. Then oxidation number. Then if needed, peripheral atom electronegativity. You have to check these. Now, if you check the structures, CF4 will have 4 fluorine atoms around that, and CCl4 is kind of similar to that one, tetrahedral shape and geometry, right? And CH2O is like this. There is a double bond with carbon oxygen, and CH4 is similar to CF4, and HCN there is a triple bond with nitrogen. These are the structures. Okay, so now you can see these are sp3, sp3, sp3. This is sp2, sp3, and this carbon is sp. Only 2 repulsion means are they are linear, right? So if it is sp3, then the S percentage is 25%. 25%. If it is sp2, it is 33.3%. If it is sp, then S percentage is 50%, because you know there are only 2 orbitals joined to hybridization. One of that will be S. So S percentage is half. That means S fraction is half. If you put it in a percentage, it will be 50%. Okay, 50%. Now you can see the one with the highest S percentage is HCN carbon. So this will be the most electronegative carbon. And then our second place can be given for this. Okay, so your answers, I think they are asking for the decreasing order. So the one with the highest electronegativity is HCN, then CH2O. Now if you check the answers, okay, you can eliminate only 2 answers, answer 3 and answer 5. Okay, answer 3 and answer 5 you can eliminate, that's it. 1, 2 and 4 you have to keep. Okay, so that means you need to think about the other 4 structures too. Okay, so we will see. Other 3 structures. Now, if you take this one for the charge, none of these carbon atoms will have any charge. Okay, so they all neutral. Here again, they are talking about the charge of the carbon, okay? Not the overall charge. Anyway, there's no overall charge and no charge for the carbon. And then oxidation number, for this one, fluorine is more electronegative, so +4. Chlorine is also more electronegative than carbon, so +4. And here, -4, because carbon is more electronegative than hydrogen. But here the dipole moments are drawn in this way, away from carbon. So now you can see this has the least oxidation number, so should have the least electronegativity. So answer 5, I mean the least place is this one. Now let's check the answers here, the given ones. So answer should be ending with CH4. Answer should be ending with CH4. So there's only one answer, right? Answer 2, me. Then this should be your answer because answer 1 and answer 4, they are ending the answer with CF4. Okay, so you can see, you can find the answer easily, right? You can find the answer easily. But according to the answer 2, you can see CF4 and CCl4 electronegativities are like this. CF4 is more electronegative. So now let's explain why. Now you can see if you take these two molecules, S percentage, charge, oxidation number, they all same. Then when we have nothing to do, we have to think about their electronegativity of the peripheral atom. So fluorine is more electronegative than chlorine. Understand? So therefore, fluorine can induce more charge on carbon. So this delta positive charge on carbon is higher. If it is having more charge, then it will be more electronegative. Okay, so therefore, this should be your answer, third place, and this is the fourth place. Anyway, that point is not needed to get the answer in this question, right? It's a very good question designed according to A-level standards. Okay, we'll see. Right. With the practice, these questions will be easier and easier for you. So do enough questions and repeat. And not if there is anything interesting, and especially if you got something wrong, you have to think about that again and again, right? And write a review and study too. Okay, so answer for the 7th question is 2. I hope it is clear. And I remember last week also we did a similar question regarding sulfur electronegativities. Check that too. That was also good. Right. 8th question. Another famous theory about photons. We'll see how to do it. In your 8th question, it's telling like this. There's a bulb which emit yellow color, and the nanometer value is given for one photon, one energy packet. There are a set of energy packets now. So these energy packets are having 590 nanometer wavelength, lambda. Okay, and they are telling if you lit this one for like 60 seconds, okay, for 60 seconds, it generate 20 into 10 to the power 20 photons. 10 to the power 20 photons. Energy packets are given, right? And they're asking, what is the energy generated per second? What is the energy generated per second? Energy per second. That's the question they're asking. Okay, right. So how do we do this one? So there is no definite formula for this one, okay? So there's no formula that changing from question to question. There's only one formula. What is that? Finding the energy of an energy packet. Planck equation equal h nu for frequency. If you replace this one with wavelength, it will be hc over lambda. This is the formula you have. Only formula, right? And using this wavelength, you can find energy of one photon. Remember, here it is giving energy of one photon. One photon is important. One photon. Because here they are talking about 10 to the power 20 photons in 60 seconds. Right? You can find how many photons in 1 second, but let's, try to derive an equation for this one, for our easiness. Now, this is the main formula you are remembering, okay? And the total energy, E total, will be what? This hc over lambda, energy of one photon, into 20 into 10 to the power 20. This is the total energy. Total energy, right? And energy per second is power. So how do we find power? You divide energy by the time. So now So if in other words, power, or you can say energy per second, how do you find it? Hc over lambda into 20 into 10 to the power 20 and divide by the time, 60 seconds. Okay, so this is the formula. Now let's substitute. Planck constant 6.626 into 10 to the power minus 34 joule seconds. I'll add units to show you something. Okay. And speed of light 3 into 10 to the power 8 meters per second. And 20 into 10 to the power 20 is there. And our, what is this? Lambda wavelength 590. So 590 is given in nanometers. So if you put it into meters, 590 into 10 to the power minus 9 meters. To simplify a little bit, 5.9 into 10 to the power minus 7 meters. Simplify, okay? And then put that value here. It will be useful. Minus 7 meters. Because if you didn't convert the units, then you can see the units will not get cancelled out finally. Okay, because final answer should be coming in joules, ne? Joules per second. And here it is 60 seconds. Right. Now, let's try to simplify. Here you have 6.6. Roughly, we are getting an answer of 3. And here you can cut these 2 zeros and into 2. Then you have 5.9, which is almost 6. And you have 6. Okay. And 10 to the powers. 10 to the power minus 34. 10 to the power 8. 10 to the power 20. And divided by 10 to the power minus 7. So if you simplify these powers, what will you get? This is 28. If you put this minus 7 upward, it will be 35. 35. So there's 34. So 110 will be remaining. 10 to the power 1 will be remaining. And here you can cut this 2 into 6 is 2 into 3 is 6. And you can cut that one to this one. And 5.9 is almost, you can say 6, no? And if you cut this, it will be 1.1. Okay, so if you multiply this one by with this 10, it will be 11 joules per second. Approximately, okay? Now check the answers. Okay, students, I hope you got that one. Any questions? Any doubts? Yeah, 11.2 is there. So that is our answer. If you actually simplify, you can see it is 5.9, no? We took it as 6, no? It will be a little bit higher than 11. Here you have one answer, 4. Answer 4. Okay. So you can do the question in this way too. You can find in photons released per second, number of photons, and you can multiply energy of one photon by that. Okay, so that method is also correct. Okay, find photons per second. Okay, then multiply energy of one photon by that. Okay, so then you will get number of photons per second. Then if you multiply, you will get energy, total energy per second. Okay, total energy per second. And if you want to remember something, the total energy, you can remember like this. Hc over lambda into n. N is the number of photons. Same thing, we have done enough questions in this theory, right? Okay, good. So what will happen with the practice like this, Lame? So we will add our, after discussing one more paper, we will resume our regular discussion. So in that discussion, we can put gases questions, energetics question, S block questions, everything. Okay, so then when we are doing more and more question, it will be normalized to you. Okay, all the lessons, topics, and you know what are the MCQ points they are asking. So then when you go to the A-level exam, you don't have any stress because you have already done what will be there in the A-level exam. Okay, so trust that process. That's my advice. Right now, you will not see the A pass some people. Okay, but still you need to trust me and trust the process more importantly and do the work as I ask. Okay, so then little by little you will get there. Right now you may have a doubt whether I can get an A here. You might think it, but my advice is follow the process. Rest will come. Okay. Then go to the ninth question. It's a good one. Which of the following statement is false regarding below molecule? So there is a molecule given. Let's see how to draw it. H, C, triple bond, C, and C double bond O, CH3. And they have labeled these carbon atoms as 1 to 4. 1 to 4. And there are five statements given about these atoms, right? And the first one, C4H bond length is longer than C1H bond. So C4H bond means here, the H bonds that are lies here. Okay, so if you take this part, there will be 3 CH bonds now. Okay, and they are comparing this one, let's put it as X, and they are comparing this one with this carbon hydrogen bond. Okay, so which one is longer? Which one is longer? So it's true that both are single bond. So it's not going to be equal also, right? Seems like equal when you just look at the diagram, but you know, bond length depends on several factors. One of that factors is, the length of the hybrid orbital. So now this carbon is sp hybridized. So this overlapping is what? Sp, or you can say sp overlapping. And here, this one is sp3 overlapping because this carbon, C4 carbon is sp3 hybridized. Understood? So then you know, if the S percentage is lower, right, and the bond length, the orbital length will be higher. If the S percentage is lower, here it is sp, sp2, sp3. So here you have more p character. More p character. If the p character is more, therefore length will be higher. Okay, so they are telling that this bond is longer. So first one will be correct. It's not the answer. They're asking for the wrong one. First one is not the wrong answer. Okay. Then the next one. Hybridization of C1, 2, and 4 atoms are sp, sp2, and sp3 respectively. C1, C4 we already found. And C3, let's go to the board and tell. This one is also what? sp2 hybridized. Why? Because there are 3 repulsion units. So trigonal planar geometry. sp2 hybridized. And this carbon is also sp hybridized. So our second answer, again correct. Then you go to the third statement. Third statement. In the third statement, out of the C1, 2, 3, 4 atoms, the most electronegative atom is C2. The most electronegative atom is C2. It's a good question, right? C2. C2 is one of the two sp carbon, right? And there are 2 carbons. So let's draw it and explain. Like this, and this is bonded to 1 carbon. And if you check the S percentage, both are having 50% each. 50% each. So S percentage is same. Then you go to the next one, charge. If you take the charges, both are having no charge. Then go to the oxidation number. If you go to the oxidation number, now you can see here it is taking 1 electron from hydrogen. So oxidation number will be -1. But here it's all carbon. So oxidation number is 0. Here oxidation number is -1, this one is 0. So higher oxidation number, higher. So therefore, electronegativity of this carbon, sp carbon, is higher. So if you arrange them in ascending order of electronegativity, okay, least electronegativity will be shown by C4, then C3, then your C1, and finally highest electronegative carbon will be C2. Okay, we got the order too. Third one is also correct. And you can see first three statements, actually first one and the third statements, you have to think a little bit. But you will see answer, it's too obvious. Okay, look at the fourth one. Electron pair geometry are same. It can't be, no, lamai, isn't it? C1, C2, C3, you saw their hybridizations are different. If the second statement is correct, okay, fourth one must be wrong. Okay, so then that kind of a paradox like thing is there. If fourth one is wrong, for correct, second one will be wrong, isn't it? So you already decided second one is true because it's very easy. And then obviously, you know, even without understanding other statements, you can decide fourth one is the wrong statement. They don't have equal electron pair geometries, isn't it? This one is having linear electron pair geometry. This is trigonal plane. And this one is tetrahedral. So fourth one is wrong. Different electron pair geometries. And we found the answer. Answer is answer 4. And the last one is also should be correct. They lies in the same line. C1, 2, 3. That's correct. You can write as the explanation. This is correct. Why? All sp hybridized atoms, all sp hybridized atoms and bonded atoms lies in the same plane. Same line. And if you talk about the same plane, you can tell sp2 both. All sp and sp2 hybridized atoms and their connected atoms will lie in the same plane. Okay, it's a good question. Answer was easy, but my point is there's a good point about bond length, okay, and electronegativity. Those 2 points are good. Yeah, now let's go to the 10th question. Out of the following atoms, okay, look at the board. I was forgot to ask you to write this one. Look at the 10th question. Out of the following atoms, the one which released least energy and the one which released highest energy at gaseous state during gaining of electrons are respectively. So gaining of electrons, electron gain energy is one of the 4 periodic properties we discussed. And it is the kind of a good periodic property. You need to learn and remember them thoroughly, right? Electron gain energy. Yeah, you can see electron gain energy will be higher. I mean, higher means release more energy. Eg1, negative value will be highest for a given period. Negative value will be highest for a given period. You can say group 17 elements. That means if you take second period, fluorine will be the highest. Third period, chlorine will be the highest. Okay. And if you take the group 17 elements along, right? Okay, for group 17, you can say chlorine is the most negative value. That means release more energy than fluorine, then bromine and iodine. The reason we discussed last week, because this atom is too small. That's the reason. So chlorine is the one which is having the optimum size. optimum size. And the problem with these two, they are very large. Okay, so now by telling and identifying those points, we can decide which element has is releasing the highest energy. It is Cl. So you have to select answers that are ending with Cl. So there are three answers. Okay, so there are three answers. What are the three answers? Second one is telling P and Cl. Third one is telling Na, sodium and Cl. And there's your fifth answer also. It is telling lithium and Ca. Lithium and Ca. Now, here's the place where things get a little bit difficult. Okay. So now I know most of you can come up to this because you can decide chlorine is the most negative value, having the most negative value. Okay. We can say now you know no, exothermic. Most exothermic or most energy is released by chlorine. But the problem is whether it is phosphorus, sodium, or lithium, the one releases the least energy. Okay, so all these three elements are exothermic. That means Eg1 is negative, release energy. Release energy. Okay, now think. Sodium and lithium are metals. Sodium and lithium are metals. Phosphorus is a non-metal. Non-metal. When you compare metals and non-metals here, you have to think. Non-metal will relatively likely to release more energy than metals. Okay. Release more energy than metal. Okay. And then sodium and lithium will release low energy. Then these two elements are there in group 1. If you consider group 1 elements, by now you have done S block also, right? So lithium, sodium, potassium, rubidium and cesium. These are the group 1 elements. So downward the group Eg1, negative value, what will happen to the negative value? It will decrease. Because the reason is the atom is getting more and more bigger. So then adding one electron is kind of not that much likely to happen because it will release less energy. So lithium is the one with the highest Eg1, highest exothermic or most negative for the group 1. Okay, so that's why we are selecting answer 3 here. The sodium is the least energy releasing atom. Understood that one now? Sodium. So you might get a little bit stuck here, so it's fine. So thinking this way, when you want to compare between sodium and phosphorus, think phosphorus is a non-metal. So then it should like electrons more. And there's one more theory I need to put here to make the discussion complete. And who's having Eg1 positive values? That means who don't like the electrons. All group 2 elements, all group 18 elements. That means noble gases because they already have stable configurations now. And then nitrogen. Nitrogen is just above phosphorus. That doesn't mean phosphorus is the least. Okay. Sometimes you might select the second answer too. But you need to understand. Anyway, nitrogen is positive, but phosphorus is negative. No? If it is negative, that negative value is kind of higher than, more negative than metals. Understand? So think like that. Okay. How many of you got the answer? This one, third one. Can I see hand raise? No, we are good. Some of you have selected. Good. Okay, write a review. I know some students might get confused between phosphorus and sodium. Lithium and sodium you should get, okay, because that was done. That should be okay. Sometimes you may have a problem with phosphorus and sodium. Now, it's a good theory point, right? And we have a small booklet for the important theories, right? And as an extra point, you can write this. Put a stand, right? And if phosphorus is considered, phosphorus will have a more phosphorus will release more energy than group 1 metals. If you consider lithium, phosphorus will have more negative value than lithium. You can check your note. Okay, periodic property note, check that one and write a statement. Phosphorus, okay, will release more energy than all group 1 metals in electron gain. Right, good. Now let's go to the question number 11. Question number 11. It's asking, consider following systems. Now it is asking about the intermolecular attractions. It's a good question. Let's review that one. So what are the solutions? Liquid nitrogen, A. Liquid nitrogen, N2 liquid. And B is aqueous rubidium chloride, RBCl aqueous. And C, aqueous CO2 solution, aqueous. And then you have D, ammonia, aqueous ammonia, NH3. Aqueous means there's water along with that, no? It's asking strength of intermolecular attractions. Strength of intermolecular attractions. Okay. Now I will quickly explain this one. N2 is a nonpolar molecule. Nonpolar molecule. Nonpolar. So liquid N2 means it contain only N2 molecules. Okay. So therefore you can say exist London forces only. London forces only. There's no other attraction. You know, London forces is the weakest attraction for if the molecule size is also small. Okay, so size is small, and you can say that too, size is also low. Size of N2 is also low. Therefore, we can say weakest. Weakest. So your answers, they are asking about the ascending order. If they are asking about the ascending order, you have to start from A, the least. Then think about the others. RBCl, rubidium chloride, is an ionic compound. Here you will have interactions between rubidium plus iron and water. Rubidium plus iron and water. It's delta negative, and this one is delta positive, and the attractions will build like this. And in the same way, you will see there will be attraction between Cl minus and positive part of the water molecule, delta positive and delta negative. There will be attractions here. So these attractions are called iron dipole attractions. Iron dipole attractions are the most strongest attractions. Most strong, or you can say strongest. Understood? So then in your order should end with B. B is the one with the highest. No argument about that. And in this way, this one, carbon dioxide AQ, CO2 is non-polar. CO2 is non-polar. And then water is polar. H2O polar. So here the attraction force you are having is from water you have dipole, dp-idp interactions. dp-idp, which is kind of in between strength. Okay, will be better than A, but not good like, this is the strongest. No? strong. And then ammonia, NH3. And ammonia will make hydrogen bonds with water, H bonds with water. So, H bonds is also a good attraction. It is the strongest intermolecular interaction. Strongest intermolecular attraction. This is most strong secondary interaction. Okay, so now you can see obviously carbon dioxide and ammonia, if you consider, ammonia will have more interactions and it will be better than carbon dioxide interaction. So this should be your answer, ACDB. ACDB. Good question, okay, Lama? Write a good review for that. ACDB. Answer will be answer 2. Answer 2. Okay, so how many of you got answer 2? Can I see a hand? It's a good question. Okay. Yeah, good. Right. Good. It's a good question. So remember, ion dipole interactions are the most strongest, okay? We did a similar question in our theory class 2. Look at the next one, 12th one. The smallest measurement of burette and the measuring error are respectively. So it's a little bit of a practical side. Smallest measurement and the error. So I'll explain that one. Of the practical side. So in burette, if you take like this. Okay, if you take like this. Let's say this is the body of the burette. Then it is having, let's label, the 0 is there at the top, right? So if you say here, let's say 10 is there, then this will be 11 and like that, 12 like that you can take. Okay, so let's say this is 11. And then the distance, this whole distance not to the scale, it is divided into it's more fair, and this space is divided into 10 parts. 10 parts. In the middle you have 5 and 2 small 5 parts. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Like that. So then the smallest reading will be this. So it is actually 0.10 cubic centimeters. This is the smallest reading. Smallest reading. So when you are writing burette readings, example, now let's say they are giving a water level like this. The meniscus is right here, okay? So this is the level you are reading. So then when you are writing it, you have to say 11.50 cubic centimeters. This is the way you have to write. Don't say 11.5. It's wrong. You have to say 11.50 because you know it exactly. Understood? Like that, write the burette reading. And then what is this error? Error. So error is explained in this way now. Now if you take a burette reading, now it's put to diagram. And here's your meniscus, okay? Meniscus. In physics, you will learn why this is curved like this. And you can read it properly. The error, now let's say this is one reading and this is one. Let's say this is 11.5 and let's say this is 11.4. Right? So this is the level. And you will be able to see exactly the middle of this one. Okay, and then now let's say the water level is somewhere here, not in the middle, but then you can say this, you can round it off to the 11.4 here. And then if the water level is somewhere here, then you can put it to the 11.5. Okay, so then the error is actually not the whole 0.01 error, 0.10 error is not there. Error will be half of this, because if it is closer to the 11.5, you can tell it is 11.5, and you will never say water level somewhere here. You will never say it is as 11.5. This is 11.4, and this water level is 11.5. So the error is less than 0.1. Error is half of 0.5. It is 0.05 cubic centimeters. Understood that one now properly? Okay. Error will be less than that. Okay. Error will be lower than that. So remember this one. So what I'm trying to explain you, if these are the two markings, 11.4 and 11.5, it should be actually 11.5 here, no? 11.5 or 11.4. Then if the water level is closer to 11.5, we can take it. Okay, and 11.4, you can take that one. So this water level, you are never going to read as 11.4 because it is closer to 11.5. So your error is not whole reading. It will be lesser than the complete smallest reading. That's why we take the error as 0.05. It's a good question. Anyway, a practical application, I think, will be important for you. Okay, haven't asked in the A-level exams over, but for your term test, this is a term test paper. No? So they can ask like this. So what is the answer then? Answer is answer 3. Answer 3. Okay, add this also to your calculation tube. Paste a small sheet of paper in the tube and mention about this one, because we did a practical about this standard solution preparing like that, and you can add this point there. Okay, about burette reading. Smallest unit is 0.10 centimeter cube. Then the error is 0.05. So that means per drop 0.05, it is increasing. You know, burette, it is, you can, if you slow down the process, it will release the solution drop by drop. No? Okay, for 2 drops, it will decrease the reading by 0.1 centimeter cube. Okay, write that too. 2 drops of two burette drops is equal to 0.10 centimeter cube. Okay, 2 burette drops equal to 0.10 centimeter cube. Right, now let's go to the next question. Question number 12. Question number 12. Sorry, 12 we did. 30. Consider the following compounds A, B, C, D, and E. It's asking for the correct graph. Asking for the correct graph. So the correct answer is answer 3. Can I see a hand raise? How many of you got answer 3 for the question number 13? So again, asking about the intermolecular attractions. Yeah, good. You can see some of you have taken the answer. I'll explain. And give me a second to put these molecules in the board. A, it has 3 carbon atoms. Sorry, 4 carbon atoms, a hydrocarbon. There's no oxygen and anything. B also kind of very similar to that one, and it is branched. Okay. And C, it is having an oxygen atom. And mass is also higher. And D and E are alcohols. You can see OH parts are there. 4 carbon and OH is there. And for this one, it is branched. Okay, right now I'll explain properly. Understand it's a good question, okay? And here, these are hydrocarbons. Hydrocarbons. So what are hydrocarbons in organic chemistry? You will learn it properly. Hydrocarbons are the compounds, organic compounds that contain only carbon and hydrogen. So hydrocarbons are considered to be non-polar. Non-polar. Understand? So then they will have London forces only. If they are non-polar, they will have London forces only. So no DP or hydrogen bonds or anything. Okay, there are hydrogen, but those hydrogen are not connected to more electronegative atom. No? So they can't form hydrogen bonds. And then these two should have a difference. No? So what's the difference? This one is branched. This one is branched. So if this is branched, you can say, if this is branched, then it will be more like spherical. More like spherical. Then surface area will be low. Surface area will be low. If the surface area is low, number of London forces will be lower. Because you can demonstrate this one using a small diagram. Now, if it is linear like this, then you can form more London forces. But if, let's say, if it is spherical like this, the surface area is very lower, then only few London forces can be formed. Understood that? Only few London forces can be formed. But this one, it's linear, so it can form many London forces. So that's the explanation for the AB. Okay, so then in your graph, how should it come? Check the graph here. A is higher, then B should have a lower value. Okay, then check about this compound. This is, I don't want to tell you the name of this one. Anyway, you will learn it later. Anyway, the name is ketone. This is a ketone. Another organic compound, and it has an oxygen atom. So this is a polar molecule, but it can't make hydrogen bonds. So it make DP and London forces. So then the boiling point should be higher than A. And you can see it's more mass also. The mass is also high. So therefore London forces will also be higher. Therefore London forces will also be higher than AB. Anyway, you can decide it should have a kind of a higher value than AB, right? And these are called as alcohols, right? And they have hydrogen attached to oxygen atom. So this can form hydrogen bonds. Hydrogen bond is a special DP attraction. So don't say DP again. Hydrogen bonds and London forces. Understood? And this one has more London forces and this one has less London forces. H bonds and London forces are lower. Why? Because this is branch. That's why London forces are lower. Understood now? So how do they make London forces? Let's say like this OH group is there. This one contains more other parts. And they will make hydrogen bonds to the lone pair. This is a hydrogen bond. It's H bond. Understood? It is, like I said in the earlier question, the strongest intermolecular attraction. So then yours D and E should have more values, and especially your D will be more larger and E will be little bit lesser. Understood? So this is there in your answer 3. Answer 3. Okay. Another good question. Right. So for the question number 13, answer is answer 3. Answer 3. Others are wrong. You can see the answer 4. Some of you might selected that one. It's wrong. It says C is the lowest. No, C is not the lowest. It's a good question anyway. And we'll discuss similar questions to this under organics actually. Because it's kind of a little bit organic related to, you can confirm these theories there. But anyway, the basic theories are coming from bonding lesson. Right. Now let's go to the question number 14. It's a small chemical calculation. Okay. It has small calculations, no redox or anything is involved there. You have just simple calculations to do. So it's asking in a concentrated ammonia bottle, following informations are given in the label. Following informations are given in the label. Here the assay is something is given, so it's actually the concentration. It's kind of old word used in chemistry. So maybe a mistake too. So anyway, don't worry. It's the kind of the percentage, how much ammonia is there. And then density, okay? Everything are given. Okay, now take a screenshot and you can write later. No? Okay, this is the answer. Okay, now shall we go to the calculation question? We have discussed all the questions now. In a concentrated ammonia bottle, following informations are given in the label. Right. So how to do this question? Where should we start? Where should we start? Where should we start? So it says, they're asking the concentration in moles per decimeter cube. Moles per decimeter cube. Yeah, over to me. Put them in the board. Give me a second. Ammonia percentage is 34%. And then density 0.8 grams per cubic centimeter. Nitrogen and hydrogen molar masses are also given. Right, now look at this one. It's not a difficult question. You can manage this. Don't worry. So the thing is, it is telling out of the total sample. So what is the meaning of this data? Out of 100 grams of total sample, 34 grams is ammonia. This is what it is telling. Understand? And it is telling again, this data is telling you mass of 1 cubic centimeter of solution is 0.8 grams. Okay, mass of 1 cubic centimeter of solution is 0.8 grams. Right. Now, when they are asking the concentration, in moles. How many moles are there in 1 decimeter cube? How many moles are there in 1 decimeter cube? Okay. So then we need to consider, let's consider 1 decimeter cube. Okay, so let's consider 1 decimeter cube. So what is the mass of 1 decimeter cube? Total mass. So you know 1 cubic centimeter is 0.8 grams. No? So then 1 decimeter cube will be 0.8 into 1000. That means 800 grams. From this 800 grams, you know, if there are 100 grams, it is 34 grams are available from ammonia. Then you can take mass of NH3. How do we take mass of NH3? 34 from 100. Okay, so then you can take the mass of NH3, right? And no need to simplify. If you can simplify, it's too obvious here. 8 into 34 grams are there. And this is the mass of NH3. Then you can find moles of NH3. Now you are finding everything for 1 mole, 1 decimeter cube, right? So concentration is simply that. How many moles of ammonia are there in 1 decimeter cube? Okay. So if you find moles of NH3, what you should do? 8 into 34 is the gram value, you know. Divide this one by molar mass. Nitrogen 14. 3 hydrogen is 370. Divide this one by 17 grams per mole. So that's why I asked not to multiply because it will get cancelled. 17 times 2 is 34. So 18 to 2, 16. 16 moles are there. So therefore concentration will be what? 16 moles in 1 decimeter cube. 16 grams per 16 mole per decimeter cube. Understood? This is the answer. So I think the answer is answer 4. Can I see a hand raise? How many of you got answer 4 for this question? It's a good one. Okay, good. Now let's go to the next question. Question number 15. Question number 15. In an aqueous solution of sodium chloride, gaseous chlorine is soluble. What are the intermolecular attractions in this system? So they are asking about the whole system. They are asking about this whole system. Aqueous solution of NaCl, gaseous chlorine is soluble. You have NaCl aqueous solution, NaCl aqueous. So that means what are the things they have here? It has sodium plus ions, Cl minus ions, and you have water molecules. You have everything, right? And it says gaseous chlorine is soluble, Cl2 gas. So then Cl2 gas also comes to this one. Then you have ions, and then you have non-polar molecule, and then you have a polar molecule. Okay, so they're asking what are the interactions that can be there. Okay, so let me tell you. So between sodium plus and water, you can't ignore that, no? Sodium plus and water, you will have and Cl minus and water, you will have hydrogen bonds, H bonds. And then between water molecules and water molecules, you will have again hydrogen, sorry, not hydrogen bonds, my mistake. Between sodium and between ions and water, you will have ion dipole interactions. Ion dipole interactions, okay? Between water and water, you have hydrogen bonds. You have hydrogen bonds, right? And then between water and Cl2, you have dp-idp interactions. And don't forget, between ions and Cl2, Cl minus and Na plus can make attractions with Cl2. Then they will have ion IDP, induced dipole interactions. Okay, so then you can form London forces too. If it is having dp-idp and London forces will also be there. So you can see basically every attraction possible is there. So what should be your answer? Let's check the answers here. Answer is answer 5. Ion dipole, ion induced dipole, hydrogen bonds, London forces, everything you can find there. Okay, so dipole is not given. Dipole is not given. Dipole is not written also. Ne? Because the hydrogen bond is also a special type of dipole interaction. So no problem with that. So how many of you got answer 5? Can I see a hand raise? It's a good question. You should be happy on it because this is the level that we are expecting from you right now. If you missed the question, don't worry, write a review and study. Go through this lesson again. If you need the recording, you can ask. We have every facility given. So use them. Right. Now let's go to the question number 16. Now here you have 5 questions, A, B, C, D, 5 questions. We'll try them. First one, it is asking out of the pair of compounds, the one with the same shape containing pairs. Okay, same shape containing pairs. Okay, the first one, answer A, gives you BRFI and XeOF4. And answer B, SOF4 and XeOF4. And answer C, BRF5, PCl5. Answer D, SOF4 and PCl5. So now you can see some structures are repeated. Okay, so if you get their shapes, restructure, then go to the shape, you can get the answer. Okay, so BRF5. So there are 7 valence electrons in bromine. Out of that, 5 electrons are gone for the bonding with fluorine. Okay, so only 2 will be remain. So that exists as 1 lone pair. So if you take BRF5, then it will have 1 lone pair and 5 bond pairs. 1 lone pair and 5 bond pairs. So then it will be like this. Okay, so what is this shape? It comes from octahedral geometry. 1 lone pair, 5 bond pairs. So total 6 repulsion units. Therefore, octahedral electron pair geometry. Then it will be square pyramidal shape. Square pyramidal shape. Okay, so like that you can decide. Then take the next one, XCF4. So xenon is having 8 valence electrons. When oxygen makes bonds, it usually makes double bonds. So you have to remove 2 electrons, and to bond with 4 fluorine atoms, you have to remove another 2 electrons. So out of that, only 2 electrons will remain. That means 1 lone pair, very similar to this one. And you have XeOF4 square pyramidal molecule. Okay, so this is also square pyramid. Same thing. So that means they are having the same shape. So answer 1 supposed to be correct. Okay, and then you have another molecule, SOF4. Sulfur is having 6 valence electrons. Oxygen make double bonds, fluorine makes single bonds. So if you subtract it, nothing will remain. So no lone pairs. So then you will have 5 repulsion units. 5 repulsion units. Like this. This one. So this is what? Trigonal bipyramidal shape and geometry. So no lone pairs for the sulfur. And if you take PCl5, that is also the trigonal bipyramidal electron pair geometry. It is a very common example we take to draw a trigonal bipyramidal electron pair geometry. So they both will be trigonal bipyramidal. So your answer D also correct. And these 2 will be incorrect, not the same. Answer A and D answer is answer 4. Okay, answer is answer 4. I hope most of you got the answer correct. Okay, draw the structures. Follow the Lewis method if this is difficult. So these are not Lewis structures. Okay? You can see the fluorine, I didn't add lone pairs. And just for the review, we are drawing this structure. When they asked to draw the Lewis structure, remember to put lone pairs on peripheral atoms too. It's very important. And let's go to the next question, 70. Which of the following statements are true regarding hybridization? Hybridization, we came across few questions earlier, sp2 like that. And let's see. First statement, hybrid orbitals are always formed by mixing of atomic orbitals with different shapes and different energies in different sub-energy levels. So there are so many differences there. So anyway, it is correct. Because why? What are the three hybridization states we study? sp, sp2, sp, sp2, sp3 like that. Now, for example, if you take carbon atom, its electronic configuration is 1s2, 2s2, 2p2. Okay, then it comes to the excited state. And this one of the electrons will be jumping to this orbital. Okay, so when they are undergoing hybridization, so these are the 2p. Those are, dumbbell shape. And 2s is a spherical shape orbital. So when they are making sp2 sp3 hybridization, all of them will be mixed. Okay, so in sp hybridization, only one of sp orbital and one of s orbital will be mixed. Okay, so it's kind of same. Okay, different orbitals are mixing, different sub-energy levels, and they are having different shapes, different energies too, because this axis is energy. Check your bonding tilt. So then you can say all regarding to everything, this A statement is correct. A statement is correct. Understand? So they, after hybridization, they are giving 4 equal orbitals. Okay, hybrid orbitals will have equal energy, equal shape. Okay. So, but the first part is, that they are different. Okay, before hybridizing, they are different. And the second statement, sigma bonds are formed by linear overlapping of two hybrid orbitals. That's true. Hybrid orbitals can form only linear overlappings. They can't form lateral overlappings. Okay. So what are these linear overlappings? Which after hybridizing, they will give you 4 equal hybrid orbitals. Like this. There'll be one more one here. If it is sp3 hybridization. So those hybrid orbitals can't form lateral overlappings. It's never going to happen, wrong. So they only form linear overlapping. So what is a linear overlapping? The overlapping happens through the internuclear axis. Linear overlapping. So A is true, then you can say B is also true. Okay, can't form lateral overlappings. Form lateral overlappings. Right. Go to the next statement, third and fourth statement, C and D statements. Look at the C. 5 bonds are formed by lateral overlappings. It's wrong. Like I said, they can't make lateral overlappings because there's only one side is there. Okay? To make lateral overlappings, it should be dumbbell shape. Two symmetrical lobes should be there. But it doesn't have, hybrid orbitals are not having two lobes. Right? In symmetrical lobes. So it's wrong. C is wrong. And the next one, sp2 hybrid orbitals can, and non-hybrid p orbitals arrange in the same space, same plane, same space in the same plane. Okay, let me explain that too. So third C statement is anyway wrong because they can't form lateral overlappings with anything, even with each other or with a p orbital. It can't form lateral overlapping. See, this is a p orbital. It's no lateral overlapping, so it's not going to work. Okay, so let me explain that same plane thing. If it is sp or sp2 hybrid orbital, Now in sp hybridization, let's take sp2 hybridization. That is easier to explain. This is energy, and earlier you have these three p orbitals and one s orbital. Okay, so when it is undergoing sp2 hybridization, these orbitals are mixing. These orbitals are mixing to form three equal hybrid orbitals, and they arranged in trigonal planar electron pair geometry. Trigonal plane. Okay, so trigonal plane. And your p orbital will be perpendicular to this. It will be perpendicular. So they are telling in the same plane is wrong. Therefore, D statement is also wrong. So good question. So what will be the answer? A, B are correct. C, D are wrong. So answer will be answer 1. So can I see a hand raise? How many of you got answer 1? It's a good question. Okay, good. One of you have asked the answer for the 12th question. 12th question answer was answer 3. Okay, answer 3. Okay, now let's go to this question number 18. Isoelectronic species. They are asking isoelectronic species. What are these isoelectronic species? What is the meaning of that? Isoelectronic means lamai, they have the same number of electrons. Simple. Isoelectron. Okay, so a list is given. Let's take the first one. SCN minus and C2O4 2 minus. And answer B, N2O and ClO minus. Answer C, CO3 2 minus and SO2. Answer D, PO4 3 minus and SO4 2 minus. These are the answers. Okay, now let's check which are having same number of electrons. Not that difficult, right? So there you have sulfur, carbon, nitrogen and a negative charge. So sulfur is having atomic number is 16. So there will be 16 electrons. And carbon atomic number 6. So 6 electrons. Nitrogen atomic number 7. And there's one negative charge, so one more electron. Okay, due to the negative charge. So total number of electrons will be 14 plus 16, 30. 30 electrons. And here, this one, 2 carbon means 2 into 6, 12. And 8, oxygen is 8. 8 into 4, 32. And then negative 2 means 2 electrons. So altogether, you will have, you can see it is more than 30. It is more than 30. 4 oxygen atoms. So 42, 44 and 46 electrons are there. So A is not an answer. Wrong. Not isoelectron. And go to the second one. N2O, 2 nitrogen. 2 nitrogen. That means 7 into 2, 14. 14 plus 8. So you have 22 electrons. Here chlorine is 70. Okay. Oxygen is 8. And the negative charge it is 1. So 18 plus 8, 26. It's again wrong. Like that, check. Okay. Don't add valence electrons, Lamai, and it will give you wrong results. If you add valence electrons, then for chlorine you are adding 7, but it's not that true. If you take isoelectronic, you have to think about the total number of electrons. That's why instead of getting 7, I got 17. Understood? I got 17. Then go to the statement C. Carbon, you have, like I said, 6 electrons, 3 oxygen, 18 to 3, 24. and with the negative charge, another 2. So 26, 32 electrons are there. For sulfur, you have 16 electrons. For 2 oxygen, you have another 16. Yeah, 32. This is correct. And do the same thing for the next one. Phosphorus, you have how many? 15 electrons. For oxygen means 32. And another 3. Negative charge, negative 3. Then 35, 40, and 50 electrons are there. For this one, sulfur 16 electrons. For oxygen, 32 electrons. And another 2. 34 and 16, again, you get 50. So this one is also correct. So answer is answer CD. If AB correct, answer 1. If BC correct, answer 2. If CD correct, answer will be answer 3. Okay, I hope most of you got the answer correctly. Good. Now, yeah, go to the next question. Question number 19, asking about cathode rays. Cathode rays. Okay, they're asking the incorrect statement. Look at the first one. E over M ratio of cathode ray is determined by J.J. Thomson. That is correct. So it's not going to be an answer. Okay, they're asking the incorrect one. E over M ratio was calculated by Thomson, and he saw that that ratio is same. Respectively, the gas you select. If you take Cl2 gas, O2 gas, H2 gas, doesn't matter. Always, E over M ratio of cathode rays will be same. What is the reason for that? You can write the reason. First, you can write this E over M ratio is same, and then write the reason why it is same. Why it is same. So A was correct for this question. Why this A was correct? E over M ratio was constant for cathode rays. Cathode rays. Why it is? Because you can say cathode rays are what? Always electrons. Cathode rays are always electrons. So no matter which gas you select, it is always electrons. So it's going to be always the same E over M ratio. So A is anyway correct. Then look at the next one. Cathode rays are green in color. That's totally wrong, Lamai. Cathode rays, they don't have any color. So say cathode rays are colorless. Colorless. But you will see green color glowings because of the cathode rays are colliding on the wall of the container. Because the wall is coated with zinc sulfide. So when cathode rays are colliding on the wall, then it will give you the green color. Okay, so that's why they seems like green, but it's not green, right? Cathode ray itself is colorless. They will give colors when the cathode rays are collided on some surface. Okay, so B is incorrect. Next one, cathode rays do not ionize gases. That is also wrong. Cathode rays can ionize gases. Okay, because of that, positive rays are formed. Can ionize gases. Therefore, positive rays are formed. Positive rays are formed. So that's wrong, right? And look at the last statement D, then we can select the final answer. It's telling about de Broglie wavelength of cathode ray traveling in the v velocity is given by. Okay, so de Broglie wavelength is what? De Broglie wavelength lambda equal h over mv. Okay, so if the 6.626 into 10 to the power minus 34 joule second is the Planck constant, and they haven't given us the mass of electron. It should be given in the paper. It is, as I remember, 9.1 into 10 to the power minus 31 kilograms. Okay, and the velocity is given as v. So if you simplify this one, The 10 to the powers only you can simplify. No? So 6.6 division 9.1 into 10 to the power minus 3 over V. Over V. Now check the answer. Check the answer. Yes, 9.1 V. 6.626 into 10 to the power minus 3 in meters. Yes, the answer you will be getting in meters because we substitute everything in meters, no? And they have to say V meters per second. Velocity also, they have to give the unit to make it right. Say V meters per second velocity. Understood, Lama? And to get the answer properly, they should be given us the mass of electron, okay? Which you don't need to remember actually, okay? I think it was given in the paper, I don't remember exactly. I typed this again, then I might have missed. But anyway, it was not there in the question area. It may be there at the beginning. So they are giving you the Planck constant, speed of light, and other data, no? And that place, this data might be there. I'll check later. So anyway, so this is correct, right? This is correct. So then your wrong answers are BC. That means answer is answer 2. Answer is answer 2. Question number 19. Answer is answer 2. Yeah. So these questions are kind of good, right? And go to the next one, 20. Which of the following are true? Get the first one. Isotopes of the same element have same number of nucleons. Isotopes of the same element are having same number of nucleons. So that is, what are nucleons? Say nucleons are protons plus neutrons. Proton plus neutron. So same element, number of neutrons are different. No? So therefore nucleons will be different. Okay, so A is wrong. You can say nucleons are proton plus neutrons. Isotope, protons are same but neutrons are different. Therefore A is wrong. Okay, so write again. First one, you have to say nucleons are protons and neutrons. In isotopes, protons are same and neutrons are different. So therefore A is wrong. A is wrong. And check the next statement. All atoms and ions consist of electrons and protons. All atoms and ions contains electrons and protons. So that is also wrong because of H plus. H plus. Right. This is wrong because of H plus. Why? Because H plus ion only contain single proton. No electrons are there. Okay, so A and B both are incorrect. B is incorrect. Why? Because H plus ion contain only a proton. No electrons are there for H plus. But other ions and other atoms, they all contain protons and electrons. Okay, so B is wrong because of H plus. And look at the C statement. There are 10 electrons with azimuthal quantum number ML0 for vanadium 5 plus ion. For that, we have to write. So vanadium, we already discussed, its atomic number is 23. So it's end with argon times 3d3 4s2. So then vanadium 5 plus. 5 plus means you are removing all these electrons, right? All these electrons. So then it is argon only. So then that means it is 1s2, 2s2, 2p6, 3s2 and 3p6. Now what they are asking is ml0 of electrons, ml0 electrons. Now here the L values are 0, 0, 1, 0 and 1. And then if you take the orbitals, and here you have 3p orbitals, an s orbital, and another 3p orbitals. And if you check the ml0, these all are ml0, the middle orbital. Now you can see there are 5 orbitals with ml0. ml0. So then ml0 you have 10 electrons. That is correct. So in this question, A was wrong, B was wrong, but C is correct. Understood, Lama? There are 10 ml0 electrons. Kind of a good quantum number and configuration question, just like the MCQ, second MCQ. Yeah, then the next one, wavelength of X-rays is less than the wavelength of microwaves. It's true. It's a very obvious question because X-rays are having more energy. X-ray, more energy. If it is having higher energy, then frequency will be lower. Wavelength, no, frequency will be higher. My mistake. Energy is equal to hc over lambda. hc over lambda. Now, if energy is higher, wavelength will be lower. You can directly say that. Understood, Lama? So, C and D are correct. So, answer is answer 3 again. Answer 3. The correct one stop they are asking. There is a small mistake in the question number. Question C here, it is telling azimuthally. It's wrong. Yeah, one of your friend told that one. Good. In the paper, it was mentioned azimuthally. That's why when I'm making it, it was accidentally come. So anyway, ML stands for magnetic quantum number. Yes, magnetic quantum number. So cut the word azimuthal and write magnetic, okay? Magnetic. Right now, you may not have the paper with you. If you're not having the paper, please write it, okay? Write azimuthal and cut. Then write magnetic. Good. There are some small errors. Don't mind about that. And then look at the statements. There are 5 statement questions. We'll quickly discuss that too. I think up to now, everything is clear to you. So last week also we discussed 25 MCQs. We'll do this one next week too. Right. Boiling point of HBr is greater than HCl. Boiling point. So now when we are discussing the boiling point, remember the shape? This one. Group 17 halides, HF, HCl, HBr, and HI. So now telling that it is telling HBr is greater than HCl is correct. Okay, so first statement is correct. You can see that. But what is the reason for having higher boiling point? The reason is in this direction, size increases. As the size increases, London forces are increasing. You have to mention about London forces. Okay, but let's see the reason they have given. It says HBr bond length is longer than HCl. So there is a true factor. That is also true. Because if you take HBr, here you have 1s and 1s and 4p overlapping. But if you take HCl, you have 1s and 3p overlapping. So you know that 4p is longer, but it is not the reason, not the bond length. You have to mention about what? You have to mention about the size and London forces. So both the statements are correct, but can't explain the first one. Cannot explain. Not explain. So answer is answer 2. If they are not explaining, you are selecting the answer as answer 2. Okay, Lama? Then check the next question. Ionic nature of KCl is greater than NaCl. Let's check that one. Ionic nature of KC and NaC. Now you can see the anion is same. So it depends on cation nature, polarizing power. So sodium plus is smaller than potassium plus. Okay. So therefore, polarizing power of sodium plus is higher. Therefore, NaCl covalent character is high, ionic character is low. Okay, so potassium chloride will be the more ionic one. So now telling that is more ionic is correct. First statement is okay. Check the two statements again. Now, the reason should be about polarizing power and other things, right? Yeah, when the cation is smaller, it has higher polarizing power. Yeah, it is mentioning about polarizing, and yes, if the sodium is smaller, then it is having more polarizing power. Because of that, it has more covalent nature and less ionic nature. Yes, second one can explain first one. Okay, so now for this question, we can take the answer as answer 1. So some might think now it is not telling about potassium. No, I like, okay, it's okay, right? Because if sodium is having more polarizing power, that means potassium is having less polarizing power here. Okay, so no issue with that. Understood, Lam? So you can take answer as answer 1. Now let's go to the next question. 23. In third period from left to right, both effective nuclear charge and shielding effect increases from left to right. Yeah, about effective nuclear charge, you can say ZDFF. ZDFF equal nuclear charge minus shielding effect. Now, across the period, let's take third period, they are telling sodium, magnesium, aluminium, silicon, like that it continues now. Here number of protons, 11, 12, 13, 14, it increases. That means Z increases. And shielding effect, sigma, shielding effect is also increasing slightly. But the effect of nuclear charge is more. Because of that reason, because of this, the sum of the difference of this will be the shielding effective nuclear charge now. Effective nuclear charge will increase gradually. Okay. So then telling that effective nuclear charge, shielding effect, everything is increasing is correct. Okay. Then check the next statement. Second statement is telling in third period from left to right, covalent radii decreases. Yeah, radius is decreasing, but it has nothing to do with the increasing, increasing this effective nuclear charge. Radius decreasing is correct, but it is not explaining the first one. So again, answer is answer 2. Okay, 23. Answer is answer 2. It can't explain the first one. Actually, radius was decreased about. Now the thing is, this radius was decreased because of the effective nuclear charge, you can say. But it's not a good one. Anyway, I hope you understand it can't explain the first one. That's a fact. Okay, so good to do these 1, 2 answers. The questions that are coming 1, 2 as answers. Those are good questions. Because you have to think not only true or false, right? You have to think about explaining also. Those are good questions. Then go to the 24th one. Orthonitrophenol and paranitrophenol. This was there in our evaluation test too. Right? Orthonitrophenol is having higher, they are telling higher boiling points, wrong. Melting point, and they are telling anyway. So anyway, my point is it is having lower. Because orthonitrophenol is what? Orthonitrophenol. Orthonitrophenol is this. And it is making We call this one as intramolecular H bond. H bond. So intramolecular H bonds are not useful for the does not help to increase boiling point, melting point. Understood? So then orthonitrophenol will have lower boiling points or melting point, and this first statement is wrong. And check the, let me draw the paranitrophenol too. It is the one with higher boiling point, because if you take paranitrophenol, it's like this, no? And if you take another molecule, it will make effectively intermolecular H bonds. Intermolecular H bonds. This will increase the boiling point and melting point. Understood? That is better. So paranitrophenol, this is para, don't mix up the words. This is ortho, and this is paranitrophenol. So paranitrophenol will have more boiling point and melting point, because they are making intermolecular H bonds. See the statement? Intramolecular hydrogen bonds. Paranitrophenol, no. Paranitrophenol is containing intermolecular hydrogen bonds. So both the statements are false. Answer is answer 5. Answer is answer 5. Okay, look at the last statement. Last question. Between iodine molecules, covalent bonds are present. Between iodine molecules. So that one is wrong. Why? Because between molecules, you have intermolecular attractions. Between molecules, you have intermolecular attractions. Intermolecular attractions. Okay. So intermolecular attractions are kind of secondary interactions. Secondary. But covalent bonds, ionic bonds, and then you can say metallic bonds, those all are what? Those are primary, or the most strongest interactions. Okay, so telling that between iodine molecules you have, but covalent bonds is wrong. Between iodine molecules, what do you actually have? You have London forces. You have London forces. Okay, weakest attraction force. Intermolecular attractions. So remember that. So first one is anyway wrong. Look at the last statement. Solid iodine is a nonpolar molecular lattice. Yes. Okay, solid iodine is composed of I2 molecules. So those are nonpolar. So nonpolar molecular lattice. So this lattice word will be explained sooner in our with our energetics lesson. So wait few days. So anyway, this was, you can do this one, don't worry. So answer 1 was incorrect and second one was correct. And that will contain right London forces. Okay, nonpolar molecular lattice contain London forces. So there are two molecular lattices. Lattice means simply arrangement of the regular arrangement of particles in the solid state. And there are two molecular lattices, polar molecular lattice and non-polar molecular lattice. Example, ice for a polar molecular lattice. That is a little bit stronger because ice will contain hydrogen bonds. And for non-polar molecular lattice, it's a good example, this I2. And it is, I2 molecules are held together with the help of London forces, which is a kind of a weaker one. So melting point of I2 is lower than melting point of ice. Ice is difficult to melt in relative to I2 because of this reason. So anyway, we'll discuss that as a summary again someday in theory class. After that, this will be more easier for you, right? So these are the answers for the last 5 questions. Okay, so we did discuss 25 questions today. I hope you understood it really well. And there were some, mostly the questions were really good, most of the questions. And write a good review for that one and study. And if there are any more important theories, you have to add them to your short, the special point booklet. Okay. Right. Then study well. If you have further doubts, you can send a message. I'll explain again. Okay. So next week also we will be doing another term test paper. Right. So study well, Amai. Bye and good night.